not yet equipped to talk about second-order differential equations. You're going to see them on tests and quizzes anyway, so we kind of have to talk about them just for a little bit. You're not going to understand where some of this stuff is coming from, but I'm going to do my best to explain why we're doing some of the things we're doing, just so you have sort of a clear picture of what's going on. So you're going to deal with second-order equations in this form, namely constant coefficients. So all that means is that A, B, and C are constant. So they're 1, 3, 5. They're numbers. They're not actual functions of t or y. Okay? So basically, what we're going to do anytime we see a second-order differential equation with constant coefficients, we're going to assume that the solutions, there are two solutions because it's second order, the solutions are going to be of the form some constant times e to the rt, where r is some fixed number. Okay? Now, that is sort of arbitrary to you, but it's not actually. If you think about it, if you think about the dynamics of the equation, that's the only solution that could exist. The reason for that is because here we have y prime, and y double prime trying to cancel each other and send the whole thing to 0. The only way that's going to happen is if we have a function that lives within its derivatives, right? Well, the exponential function is the only known function, the only known elementary function that we know that can do that, right? If you have e to the 5t, its derivative is 5 e to the 5t. Perfect candidate for what we're trying to do. Okay, so the way we're going to solve it is we're going to assume that the solution is of this form, and then plug it in. I dropped the c just because we're going to add this constant at the end. But for now, we have e to the rt, we drop it in for y, then we derive it once and the r pops out, and we drop it in for y prime, then we derive it again, and we have r squared, and we basically substitute it in for y prime, and y double prime. Now e to the rt's cancel each other out, and all we're left with is ar squared plus br plus c equals 0, which is just a quadratic equation. Pretty easy to solve. So we go ahead and solve it, and from then on, there's a couple cases. One is that you get two perfectly fine real solutions. If that's the case, then perfect. Your entire, what's called your general solution, will be of the form e to the r1t, where r1 is your first root and r2 is your second root. So you're going to have e to the r1t and e to the r2t, and then you're just going to multiply them by two constants, where that constant could be anything, and you just add them. So again, these two are going to be literally C1 and C2 in your answer. They won't be actual numbers, but R1 and R2 will be. Another possible outcome of solving this equation, this quadratic equation, would be that you get repeated roots. If you get repeated roots, you probably did something wrong, because at this point we're not ready yet to talk about repeated roots. But another outcome is you could get imaginary or complex solutions. If it's complex, again, you did something wrong because we're not ready to talk about them, but imaginary, you can. If they're purely imaginary, meaning there is no real part, then your solution is going to be of this form, where r is just, remember how imaginary roots happen in pairs, so if you have 4i, there's going to be a minus 4i. Well, you just take the 4 and plug it in, and you just put it into the sine and cosine function, multiplying by constants, and there you have your general solution. But that's really sort of vague and abstract, so let's go ahead and do an example, do a couple examples to see how this works out. So here we got y double prime plus y, 5y plus 5 equals 0. I immediately notice that it's a second order differential equation with constant coefficients, and say, okay, well, I'm going to assume that my solution is going to be of the form y equals e to the rt, plug it in, do my business, and I'm always going to get the same thing. I'm going to get an r squared plus 5r plus 5 is equal to 0. The only thing that is dependent on case from case, is different from case to case, is these three numbers. Here it's just a 1 by 5 because of these three numbers, right? If you don't understand where this came from, watch this part again to make sure you can follow it from here on. So I got r squared plus 5r plus 5. I can factor that pretty easily. r plus 1 and r plus 5. So r is going to be -1 and -5. Okay. Okay. So those are my two roots. They're both real. Perfect. I'm in business. My solution is going to be of this form. I'm going to have an e to the minus t and an e to the minus 5t. Those are my two roots. And then I'm going to just multiply them by two constants and add them together. And there's my general solution. Right? If you were asked for two different solutions, you can just give them e to the minus t and e to the minus 5t. Or if you're asked for the general solution, you give them this, which is any solution that in the entire universe that could satisfy this equation. So let's go ahead and do one that's a little different. Y double prime plus 9 is equal to 0. I don't know how to factor that, let's say. So I'm going to use a quadratic formula. It's going to be minus b, b is 0 here, so 0, plus or minus square root of b squared, again 0, minus 4ac. 4 times 1 times 9 with 36, all over 2 times a, or 2. So this is just going to be minus 36, and the square root of that is going to be 6i, right? 6i plus or minus over 2, or plus or minus 3i. So those two are my roots. They're imaginary. So I know my solution is going to be of this form. So what am I going to do? Well, your solution, you can literally just go ahead and write your solution. Here, let me give myself some more space. Your solution is going to be cosine of 3t and sine of 3t. Again, because the 3 was your root, right? Your repeated imaginary root. And then you just multiply them by two constants and add them together, and there you go. That's your general solution. And these two, although they look different, but the reason we assumed that that our solution was going to be of this form is because when you plug in something imaginary into this equation, you get e to the, let's say, if you use this example, e to the 3it. If you remember Euler's formula, it said when you have exponentials with imaginary arguments, so something like e to the 3it, that is actually equivalent to cosine of 3t plus I sine of 3t. If you don't remember Euler's formula, make sure you look it up and you're acquaint yourself with what it says, because you're going to use it a lot in this course. But that's basically where this form comes from. And really, although this is a little weird of a section to put here, but we have to deal with it. So there you have it, second order differential equations with constant coefficients.